Okay, so we're talking about logarithmic functions again, and we're now on to section 6.4 of chapter 6. And before I get into too many details of 6.4, let me go ahead and point out some wonkiness that's going on with Edfinity that I had to sort of change a couple problems. So you may have to go back and sort of look at yours and see if yours needs to be updated. But there were two questions in Edfinity that were doing some weird sort of stuff. So let me see if I can show it to you. Okay, so the first one was question number 11. And what you're seeing on my screen here is not probably what you got if you had already started the homework assignment. But if you haven't started, then you'll see something that looks like this. And you'll want to write it out in logarithmic form. And if you're following along with what we were doing last time, you would say, okay, well, x would be equal to log base 4 of 6. And you hit submit here, and then it would mark you wrong. And you'd say, okay, what's going on here? I clearly was following along with what we were saying in class, and I just rewrote it, and it looks like the right thing. And so you might sort of look at some variations or hit the try again button. But one thing that you should be aware of here is that there's also sometimes this help button here on the side. And this is sort of a nice lesson here because I mentioned to you that most of the time people will use log as the log base 10. But here's an example in our homework where we need to be a bit careful. If we click on this button here, this little link, then it tells you some information here about for this question, not every single question, but for this one, and you should sort of click on these links because the author, which depends on who wrote this question, is using this setup. And here it says in this question, log of x is the exact same thing as the natural log of x. So here they're breaking sort of with the tradition that we were talking about, and other places online do this as well. So if you use some graphing calculators online, they'll use this notation. So here they'll use natural log of x or log of x, and they'll mean the same thing. And then they say, okay, well, if you want to use base 10, you're going to have to write it out. And they say, okay, use log 10 of x, and not the subscript like we saw in our last one, but just log 10, or even the word log 10 of x, right? But then they say, okay, if you want to work with any other base, then use one of these two expressions. And they're the same here because the Edfinity is treating log and natural log as the same for this particular question. But the idea is this: the log base b of something like x can be computed, right, or be entered into the system in the following way: the natural log of x divided by the natural log of b. And actually, this is a really nice formula that we'll study in future sections, so it shouldn't have come at this point in the homework yet. But nonetheless, this is a nice way to compute the log base b of x. And most calculators won't have a base b function for the log. They'll just have a natural log function and a log function, and you can always use this formula here to compute a log base, a different b, right? Okay, so here, if we wanted to plug in what we were talking about previously, we'd need to put it in this format. So let's go back and try and do that. So we'll hit the try again. And here, instead of log sub 4 of 6, we'll write it out as what they were saying. So they're saying, okay, try and write it like this: log of 6 divided by log of 4. And you'll notice that I used ln here, but it doesn't matter what base log you use. You can use log base 10 or the natural log or whatever you would like. This formula is called the change of base formula. And again, we'll talk about it in some more detail, but here I'm going to just use log as they suggested in this little outline here. So right here is what I'm talking about. And when you submit it in that format, it marks it as correct. Okay, and it's not the case for every single one of these. If you look at this one here, I think, maybe not this one, but there are other ones in this section where you can just write them in this format and it'll be correct. But the thing to be aware of is that this help button exists, and you should sometimes click it, okay? So that was number 11. And then the other one that was incorrect, it had a typo in it, was 22. You could probably have gotten the answer if you were just sort of like clicking the practice a similar one, because there was a typo in the similar as well. But hopefully it looked sort of wonky to you. But I fixed that one up. And if you already tried it, you maybe can go back and try it again just to get some good practice. So that's 22 and 11 on the previous homework assignment. So be careful about how you input those base B logarithms. And some questions will ask you to do this. The way that you'll figure out is to look at that little help thing on the side and see if that's what they're asking. And definitely number 11 is one along those lines. Okay, so now that we've sort of talked about logarithms and section 6.2, let's now move on to section 6.3. And just like, you know, pretty much with every case, we define something, look at how to evaluate it, think about it as sort of a function, and then once we have thought about it as a function, we ask ourselves, well, what does the graph look like, right? So here we're going to do the same thing. We've defined the logarithmic function, and we want to ask ourselves, what does the graph look like? And not only what does the graph look like, but what happens when we translate it, right? So we can shift it up or down, left or right, we could stretch it or squeeze it, and then we can do some reflection. And we just have to remind ourselves of how we define the logarithmic function. At the beginning of class last time, we took some time in Desmos to realize that the definition came from the fact that the logarithmic function is the inverse of the exponential function. And so its graph is just a reflection across the line, y equals x. And from that information, we could tell a whole lot of things, like, for example, the domain of a logarithmic function and the range where it has a vertical asymptote and various other things, right? And today we're going to talk about some of the key features and the key points that were showing up in that discussion and how we can use them to graph it and how we can use those key points to then graph shifts without any sort of calculator. And this may be something that you'd have to do on a exam, because we may give you sort of an empty graph there, and then you have to sketch in the details of the logarithm, and you won't have a graphing calculator. All you have in front of you is just sort of a regular calculator to evaluate some points. So let's talk about how to do that. But I guess the learning objectives I should mention are, you know, identify the domain, and part of that is the vertical asymptote of a logarithmic function, and the range, and then just graph them, right? So there are two key points typically that we'll look at when we're graphing these logarithmic functions. And let me go ahead and write those out just really quickly so that you can keep them in mind, because I think they're probably the most important part of that second objective. So let me just put up the board really quickly. I'm going to put up two equations, b to the 0 and b to the power of 1. And this is true for any base b that's positive and I guess not equal to 1. So we're assuming b is not equal to 1 either. So what is b to the 0, right? Anything to the 0 power is what? That's a question for you guys in the chat. So it looks like some of you are saying 0, some of you are saying 1. Okay, well, let's try this one, and then we'll talk about what this one is, right? Because it sort of fits the pattern. B to the 1 is a little bit easier for most people. What's B to the 1? Well, let's think about b squared then. So b squared is b times b, right? You multiply b by itself. So yeah, b to the 1 is just b, right? 2 to the power of 1 is 2, 2 to the power of 3 to the power of 1 is 3. So anything to the power of 1 is just b, right? Okay, and then to get to b squared, remember this is what we said. If we increase the input by 1, we multiply by an extra b, right? So that's why we get b squared here. So if you are increasing the exponent by 1, you multiply by b. When you go in reverse, you're dividing by b. So if I take b and I divide it by b, what should I get here? Right, so again, we're dividing by b. And then to go this step here, we divide by b. Okay, we get 1, right? Okay, good. And then let's go back one, just so we're all like seeing the pattern here. B to the negative 1, what happens there? We divide by B again, and we get 1 over B, right? So B to the negative 1 is 1 over B. Okay, so to go increasing 1, we're multiplying by B, and to go down by 1, we're dividing by B. Again, that was just sort of the key feature of exponential growth. Okay, so these two equations, this is what I was trying to get at originally, are true. Anything to the power of 0 is 1, and anything to the power of 1 is just itself. Okay, and these two key facts are going to help you graph a logarithmic function. So let's convert this over to logarithmic form, and I'll just say the base here is b. So what does the equation look like? What do we get for this one here on the top? The log base b of what is equal to what? And you could just write out the whole equation. Just log b parentheses, what goes in the parentheses? Yeah, there we go. So the exponent comes to be the output, right? This is the new output, and here it's 1. And the point is just that if you take the log of 1, you will always get 0 for any base whatsoever. So anytime you compute the log of 1, you can try it in your calculator, right? You're going to get 0, and that's because b to the 0 is just equal to 1. And it's for any b whatsoever, right? Any positive b. Let's convert this one now. So again, the base is b here. What do we get here? What goes on the inside of the parentheses? What goes on the outside over here? Remember, it's the exponent that goes on the outside, and what's on the right-hand side of the exponential equation that goes on the input. Okay, so that's one, yeah, log base b of b is 1, right? What do I have to raise b to a power of to get b? Well, it's b to the 1. B to the 1 is equal to b. So these two pieces are going to be really important when we're looking at the function f of x is equal to the log base b of x. Because what it's telling us is, for example, when we plug in 1 into this function, we're going to get 0. So the point 1, 0 is always going to be on the graph, no matter what, right? Anytime you plug 1 into a logarithmic function, doesn't matter what the base is, I'm going to get an output of 0. That's this. So that's a key point on the graph of a logarithmic function. The other key point is coming from here. What does that ordered pair look like? It's not the point 1, 0. What is the ordered pair in that case? And it depends on b. Well, it's not going to be just 0, 1, so it depends on some value of b. We want to know what are we plugging in for x and what's the y value. So here the input was 1, so the input was 1, and the output of the function was 0. So 1, 0 is on the graph. Well, the input here is going to be what? So that's the input of the function, is the x value. It's going to be b1. Yeah. So the input here is b, and the output is 1. Okay. So again, if I compute f of b, I get 1, and if I compute f of 1, I get 0. Okay. These two key points are going to always be on the graph of a logarithmic function. And once you graph those 2 points, you can just sort of you can sketch in exactly what the logarithmic function looks like. And all they are just a reflection of this. B to the 0 is 1, and b to the 1 is equal to b. Okay. So let's just come back to this piece. We're going to see this showing up again, and I'll put it on a slide so you can write it down if you're sort of following along. Okay, so here again is what we're doing, right? So just a reminder here, we started with a logarithmic function. In this case, the b is 2, so it was increasing. And we said it passed the horizontal line test, and we reflected it along line y equals x, and we got this new function over here that passed the vertical line test. And we defined it to be the logarithmic function, okay? And that's what we were doing last time. Basically, anytime we were converting back and forth between exponential form and logarithmic form, we were just sort of jumping back and forth between these two graphs, right? And in a sense, we were defining exactly what it means to compute a logarithm. Now, one thing you should notice directly from the graph is that the domain and range swap with an exponential function. The domain of an exponential function is negative infinity to infinity. So that means the range of this logarithmic function is negative infinity to infinity. The range of this exponential function is 0 to infinity, the positive numbers. So the domain of a logarithmic function is just the positive numbers. You'll notice that this graph here in orange, the logarithmic function, doesn't appear anywhere on the left side of the y-axis. You cannot plug in a negative number into a logarithm. And you could try it on your calculator. If you tried to compute the log of -1, it would just tell you error, right? It doesn't know what you're asking for. And that's just a reflection here of the fact that the domain for a logarithmic function is positive numbers. You can only plug in positive numbers. And this is going to be really important to determining the domain of a logarithmic function, which is something that'll probably pop up here or there on the homework and maybe on a future quiz in the course. Okay, so let's also think about this fact here that I was talking about. You'll notice that the point 1, 0 is definitely on this graph. That point is on any logarithmic function no matter what, right? And here it's just from the fact that 2 to the 0 is equal to 1. And then the other point that's always on the graph is B1. So here the B is 2, and that's that point right here. So once you know those 2 points, then you just sort of connect the dots with the graph. One last thing that we can see from this picture is that the horizontal asymptote that we had for the exponential function, when we reflect along this line y equals x, turns into a vertical asymptote for the logarithmic function. So this logarithmic function keeps getting closer and closer to the y-axis, and it just follows it out towards infinity. Okay, so let me just now put it all down as something that you can write down. And I'll give everybody just a couple of moments to start the process of writing this down. I'm going to say a few things and highlight a few things, just reminding you of what we've just said. And then I'll ask you guys to just give me a thumbs up whenever you've had enough time to write down all the details. And here we're just starting out with the basic logarithmic function with base b. And that's going to be our parent function. Later on, we're going to sort of shift it up and down and left and right and do some reflections with it. But for now, we're going to just think about the properties of this guy. So I'll give you a few moments, and I'll say a few things and just highlight some of the stuff that we've already said. And then I'll let you have some time from there. Okay, so let me just go through this and say a few things, and then I'll ask you guys to give me a thumbs up. And I've already seen that at least one person's ready to go on. So first observation is the graph we got for a logarithm is going to be 1 to 1. It passes the horizontal line test, and that's because the exponential is its inverse. We hadn't quite said that yet. We saw that the horizontal asymptote from an exponential function turns into a vertical asymptote at x equals 0. okay? And really, you should think about it as being at the place where the input of the logarithm is 0. So here it says x equals 0, and it's just because we haven't applied any transformations yet. Another thing we saw was that the domain is only the positive numbers, okay? So those from 0 to infinity. We can only plug in positive values for the input of a logarithmic function. If we tried to plug in something that was negative, it would give us an error. So the domain is 0 to infinity. Because of the relationship to the exponential function, the range is negative infinity to infinity. And the graph, when you look at it, looks like it almost maybe has a horizontal asymptote, right? It maybe goes sort of like it's flattening out here, but it doesn't. It goes through all possible y values, all the negative ones and all of the positive ones. Okay, so the range is negative infinity to infinity. The x-intercept is always going to be 1, 0. That's the key point I was telling you about, right? If you plug in 1 for the value of x in this function, the output is always going to be 0. And remember, that is exactly what we were calling an x-intercept, the 0 of the function, okay? So the point 1, 0 will always be on the graph, and that's where it hits the x-intercept. Sometimes we're going to move that up or down or left or right or stretch it around, but for the base function, the parent function, 1, 0 is always on there. And then the other one that we had was when we plug in b, right? When we plug in b into our logarithmic function here with base b, the output is 1. And so the point b1 is always on the graph of this log base b of x function. And once we have those 2 points, we can just sort of draw an increasing logarithmic function or a decreasing one, right? And what do we know? Well, we know that if b is bigger than 1, it'll be increasing. And if b is in between 0 and 1, it's decreasing. And that's just because of the same sort of thing is true for the exponential function, the corresponding exponential function as well. And there will never be a y-intercept because the y-intercept is a vertical asymptote. It has a vertical asymptote where x is equal to 0. Okay. And it looks like everybody's already given me the thumbs up, so I think I'll just move on to the next slide here, and we'll do an example. So here we've got a base function of the log base 3 of x, and then we have a transformation. So we're going to start off with our base function being y equals the log base 3 of x, and then we're going to transform it into a different function here. What's the transformation that we're applying here? Are we moving up, down, left, right, and by how many units to get to this function f of x is equal to the log base 3 of x plus 4? So this is just a quick review of, yeah, remember when we add 4, it moves us sort of, in some cases, sort of counterintuitively to the left, and in this case, it would be by 4 units, right? So this is going to move us 4 units to the left. And we should already see that then that vertical asymptote is going to move from x equals 0, 4 units to the left, to x is equal to negative 4. So the vertical asymptote is now going to change to a different spot than if we were just looking at this one here. Okay, and let's just go through and sketch this one first, and then after we're done sketching it, we'll move sort of the key points over there. So here, let's talk about the 2 key points that we need on the graph. One of them is always the same, and again, this is for this function up here, not the one over here that we're going to shift. There's one point that's always the same, that's the x-intercept, but what is the other point in this case, right? Remember here, the log is base 3 log. So I'm asking, what are the ordered pairs, right? What's this ordered pair here, and what's the ordered pair that goes here? Okay, so one of them is always the same, 1, 0, because when you plug in 1, you get out 0. And then the other one is just when you plug in the base, 3, you get an output of 1. right? So these 2 points are on the graph of this guy. And then the other thing we should know is there's a vertical asymptote at x equals 0. So let's just go ahead and now sketch the graph of this guy. So here is our x and our y axis now. And I'm going to zoom out so you can see the whole graph. And I'm going to put on these 2 points, right? So this is the point 1, 0. So here's 1, x equals 1, y equals 0. So that's that point right there. That's the x-intercept of every logarithmic function. Then I'll just point out there's a vertical asymptote at x equals 0. That's the y-axis now. I'll put that there as a dotted line in red. And then the other key point is 3, 1, right? So here's x equals 2, x equals 3, there's y equals 1. So this is the point 3, 1. So when I plug 1 into this function, I get an output of 0. When I plug 3 into this function, I get an output of 1. And now we just realize that it's increasing because the base here is a number that's bigger than 1. And so it increases to the right. It passes through these 2 points. And then there's a vertical asymptote here dropping down in this direction. Okay, so this is the graph of our base function, y equals log 3x. Okay, so base 3 of x. And now what we're going to do is we're going to shift this whole graph 4 units to the left, right? So I'll just draw that graph now over here. And again, what we're doing is this whole thing here, right? So what's going to happen is that vertical asymptote is going to go 4 units to the left. So let me draw this a little more carefully. Here's -1, -2, -3, and -4. And that vertical asymptote that I had in red there is now going to be here at x equals -4. Okay. This point at 1, 0 is now going to move 4 units to the left. Okay, so what's going to be the new ordered pair, right? Where is it now going to be located on this graph? Yeah, so the y value there is going to still be 0, and the x value we're subtracting 4 from, and if I subtract 4 from -1, I get moved to this point over here at -3, 0. So this point here gets moved to that one, and let me just do it in blue so you can see it's a different graph here, right? So this is now this new point here at -3, 0. And what about the point 3, 1, right? What happens there? The y value is going to stay the same, but what happens to the x value? Where's the new x value going to be at? Yeah, it's going to be at -1, because if we subtract 4 from 3, we get to -1, so we're going to get to -1, 1. So this point now moves 4 units to the left over here to -1, 1. And again, it's just an increasing function that has this vertical asymptote here next to the line x equals -4. And this is now the graph of this function here. So now that we have the graph, let's answer a few questions here. First off, we can see what the domain is. In interval notation, what's the domain? Remember, the domain is the possible x values. So where are we going? It's the smallest x value and the largest. Well, remember, as we come past this point here, we can go to values that get closer and closer to -4. Yeah, so we can go all the way up to -4, but we don't include -4 because it's a vertical asymptote for the logarithm in this case. So the domain now is going to go from -4 all the way up to infinity. And we put a open parenthesis there to just include the fact that we're not including the -4. What about the range? What's going to happen here with the range? Yeah, it's going to be -infinity to infinity because it's a inverse of an exponential function. And an exponential function has a domain, which is -infinity to infinity. So even though it looks like it's sort of flattening out, it's still going to increase more and more and more, right? So there's the domain, there's the range, and here is the formula for the vertical asymptote. Okay? So let me just go back to the statement of the question so you can see it. It's asking us, sketch the parent function. So here's the parent function, along with the graph. So here's the graph in blue. And then include key points. So here's the 2 key points here. Here's the 2 key points there. And finally, identify the domain, range, and asymptote. Domain, -4 to infinity, not including -4. Range, -infinity to infinity, those are the y values. And then we had that vertical asymptote right here at x equals -4. Okay, so shifting to the left or the right is really one of the toughest things to do with a logarithm because it's going to change the domain and the vertical asymptote. If we were to just shift up and down, then things don't really change at all, right? The range is not going to change. The horizontal, the vertical asymptote is not going to change. It's not going to move to the left or right. So vertical shifts up and down are a little bit easier to deal with. So just as a reminder of what I just said here, let's say we start with a function that looks like this, log base b of x. It's got 2 key points, 1, 0, and b1. And we're going to shift to the left by c, right? So we're going to look at a new function, g of x, which is log base b of x plus c. And what happens is this point gets moved to the left by c units. So we get to the point b minus c1. And this one gets shifted to the left by c units. So we get to the point 1 minus c0. And then you just sort of sketch this in, right? And the only thing that you have to keep in mind here is that it's increasing, because this graph is increasing, and where the vertical asymptote is. And this vertical asymptote got moved over to the left by c units, so it's just at x equals -c. And that's exactly what we saw in this example over here, where c was equal to -4. And then the domain goes now from -4 to infinity. The range remains the same. So this is what's happening with a shift either to the left or the right, right? I mean, this is sort of explicitly going here to the left in the picture, but if the c was sort of a negative number here, you had x minus 4, then we would go to the right. And that vertical asymptote would go over to the right instead of to the left. Okay, so those are shifts left and right. And now let's talk about what happens when you go up and down. So here we've got another logarithmic function. And it's being shifted up by 2 units. So let's go through and solve that. Okay, so again, they're just asking us to start with the parent function and then go from there. So here I'm going to sort of draw in the parent function being log base 2 of x. And then once we have it, we'll shift the whole thing up by 2 units. So we're going to want to include our 2 key points. One of them is always the same. When I plug x is equal to 1 in, I get an output of 0. But the other is going to be different. So what's my other key point in this one? What else do I know is on this graph? Yes, 2, 1, right? So when I plug the base in to this formula, then I'm going to get an output of 1. So I know 2, 1 is there, and then I know there's a vertical asymptote at x equals 0. So that's this dotted line here in red. And then we'll just add on these 2 points. So here's this point x equals 1, y is equal to 0. And then there's this point x is equal to 2, y is equal to 1. So that's this point here. And again, the base is 2, it's bigger than 1, so it's increasing. So we just have to draw a function that's increasing here. And then it gets closer and closer to our vertical asymptote there. So this would be the graph of y equals log base 2 of x. But what we want to do here is actually shift this guy up by 2 units, right? So that's what we would call the parent function when they're asking graph it next to its parent function. That's what this one here in white is. And that's the graph of this function. Now we're going to add 2 to it. And remember, adding 2 to the outside here, not on the inside of the parentheses, just shifts the whole graph up by 2 units. The y values increase by 2. So here the x values will stay the same, and the y values will increase by 2. Last time the x values decreased by 4 because we were shifting to the left, but now we're going to be going up, so the y values are going to increase by 2. So this y value is 0, and when I increase it by 2, I get up to 1 and then 2. Right? So this point gets moved up to the point 1, 2. Okay, that's the new key point for our shifted function. And then this point here at 2, 1 gets shifted to where? What's the ordered pair for the new point? Yeah, it's going to be 2, 3, right? Because I increase this value by 2. The x stays the same, and the y value increases by 2, so it goes to the point 2, 3. So here's a y value of 3, and we go now up to the point 2, 3. Okay, and now what we want to do is recognize that we still have a vertical asymptote, right? Because that vertical asymptote hasn't moved left or right. It still stays in the same spot. We still have a function that's increasing, so it's going to look like this as it goes to the right. But then as it comes to the left, it has to get closer and closer to that vertical asymptote. And so it gets closer and closer to the other function. All right, and so here we've included the 2 key points. And now we can go ahead and write down the range, the equation for the vertical asymptote, and the domain, right? So the domain here is maybe the hardest to think about. What's the domain in this picture? What can we plug in for x? And we'll think about it in interval notation. Yeah, it's just 0 to infinity. So the domain is 0 to infinity. And again, it's simply because you can't plug in anything here other than a positive number, right? So here, the things that you could possibly plug in are these things from 0 to infinity. Okay, and then the range, because it is the inverse of an exponential function, is negative infinity to infinity. And again, that's just a reflection of the fact that it goes all the way down here to negative infinity and then up all the way up to positive infinity. So it goes through all possible y values. And then the vertical asymptote was here in red. So this vertical asymptote is at x equals 0. Okay. And the last one that we had was at x equals -4. That's because there had been some shifting left and right. Okay, so it turns out that you don't have to actually graph it to get this information over here. So we'll talk a little bit about that on some of the next exercises that we're doing. But for now, we'll just say that if you graph it, you can get that information pretty easily. Okay. So let's just draw a picture like we did before, pointing out what we said before. So you start with this function here in blue, which is the log base b of x. And then you shift it up by d units. And all that happens is this point goes up d units, and this point goes up d units. So I'm not sure why they're including these 2 points over here, but you should have included this point and this point right here. And then you still have that vertical asymptote that stays at x equals 0. Okay. So that information down here is that that vertical asymptote stays at x equals 0. The domain is still 0 to infinity. And then the range is also negative infinity to infinity. So vertical asymptotes really don't, vertical shifts up or down really don't do much to the graph, right? So they just move the 2 key points around. So keep track of your key points. Okay, so we've talked about shifting left and right. We've talked about shifting up and down. Let's talk a little bit about an example where we're just going to do some stretching. And in this case, it's log base 4 of x. And I'll just ask you guys really quickly to go through and tell me what the 2 key points are here. So what are the 2 key points that we should be looking at? And this is for the parent function, right? So let's forget about the 2 on the outside first. The base here is 4. One of them is always going to be the same, and it has an x value of 1. And the other is always going to be the same, well, not the same, but it's going to be dependent on the base, and the input is the base, which is 4. So what do we get in this case? Yeah, so it's always going to be 1, 0, and then when we plug in 4, we're going to get 1, right? But that's the key points for the log base 4 of x, and it doesn't include the 2 out in the front, okay? So here, we're going to have to stretch the y value by 2. That's what that multiplication is out on the outside. And it means that we'll go from these 2 points to some different points on our graph, right? So we'll multiply the output by 2. So here, this point at 0 is just going to be 1 for the x value, and then for the y value, it's 2 times 0. So it just stays at exactly the same point. On the other hand, this one here, where we plug in the 4, instead of getting an output of 1, we're going to have to multiply the output by 2, right? And so it's going to be 4 for the x value, and then 2 times 1. 2 times 1 is just 2. So now we'll have this second point. So here's x is 1, 2, 3, 4. For the sort of normal log base 4, the output would have been 1, but here, because we're multiplying by 2 and stretching it out, it's now going to move up to a value of 2. So there's our 2 key points for this function, and I guess I should also include the parent function as well. So let me go ahead and say, okay, there's also a vertical asymptote here that we should know about, an increasing function because the base is 4, it's greater than 1. And so here is a sketch of our function f of x is equal to 2 log base 4 of x. And then we should include the parent function as well, I guess. It's asking us to include the parent function here. The parent function would have just been, the log 4. And again, the only difference would have been that instead of 4, 2, it would have been 4, 1. So that would be this point right here. It would still pass through this guy over here, and so that function looks like this. Okay, so this one would have been y equals log base 4 of x. All right, so there's those 2 functions, and we can write down the domain, the range, and the asymptote. The domain is going to still be 0 to infinity. The range is negative infinity to infinity, and the asymptote is x equals 0. So the same sort of stuff before. When we're just stretching, it doesn't change the location of the asymptotes, the domain, or the range. Okay, so that's another good one where we're just sort of going through less steps than we would have in the previous examples, but we identify the key points, move them according to the transformations, and then sketch in any vertical asymptotes. Okay, so here's one where we'll need to do a couple of steps, and I want to show you sort of a shortcut here where you don't have to actually sketch the graph if you want to find where the vertical asymptote is, and also the domain. So there's a shortcut to finding the domain and the vertical asymptote. And it has to do with the input of the function, okay? So here, when I'm looking at the logarithm, what's between the 2 parentheses there of the logarithm is x minus 2. So that means we're having a shift to the right by 2 units on the graph. But in terms of the domain, we can sort of think about it the same way that we would have thought about a square root function. So if we would have had the square root of x minus 2, we would say something like this. Well, x minus 2 had to be greater than or equal to 0. In this case, we can only plug in things that are positive, so instead of greater than or equal to, we just have a greater than. So to find the domain of a logarithmic function, you could just take whatever's on the parentheses there of the log and make sure that it's positive. And then you go through and you solve this inequality, right? So you add 2 to both sides, and you get x is greater than 2. And then to write down your answer, we typically write it in interval notation. So what's the interval that is represented by x is greater than 2? How would we write that down? Yeah, it'd be 2 to infinity, right? And we would put a parenthesis here because it's not greater than or equal to, it's just greater than. So this would be the domain, and we can see it without ever actually thinking about the transformations or anything like that. Just what are we plugging into the logarithm? The same thing for the vertical asymptote. So for the vertical asymptote, what's happening is, just like when we were looking at a rational function, if the denominator of a rational function was ever 0, then we'd have that sort of blow up to a vertical asymptote. Here, if the input to a logarithm is ever 0, then we're going to have this sort of blow up that we're having in the picture, right? In other words, to find the vertical asymptote, you set that thing between the parentheses equal to 0. So in this case, you would get x minus 2 is equal to 0. And so we can see that indeed the vertical asymptote moves 2 units to the right. That's what x minus 2 does, right? So from x equals 0 to x equals 2. So we can write down the domain and the vertical asymptote without ever actually like thinking about the graph. And the range is really easy. What's the range going to be in this case? Yeah, it's going to be negative infinity to infinity, and that's just because it's the inverse of an exponential function, right? And the domain of an exponential function is negative infinity to infinity, so its inverse, this logarithm function, has a range from negative infinity to infinity. And we don't even really have to care too much about what's going on here with the shifts up or down, because it stays negative infinity to infinity, right? If I move that range up or down, it stays negative infinity to infinity. Okay. So that's how you would solve this problem without any graphing. And I think we've done enough graphing here that I'm going to leave the graphing part up to you guys and to try that out. And then I'm going to sort of do 2 more problems. I think 3 maybe? Yeah, 2 more. After I talk about the last 2 transformations. So the last 2 things we can do is if we replace log of bx with the negative log of bx, what it does is it rotates us across the x-axis, right? So we can flip across the x-axis. Or we could have replaced x with negative x, and what that does is it changes us to rotating across the y-axis. This one is particularly difficult because the domain will now change from negative infinity to 0. But you can always just set what's inside of the parentheses greater than 0 and then go through and solve, okay? So that's just sort of flipping around. And here's an example where we have all of the different types of transformations. So here we've started with a base function, a parent function of log base 3. So that has key points 1, 0, and 3, 1. And then we're going to move 4 units to the left. Once we have 4 units to the left, we're going to rotate across the x-axis. That's what the negative out in the front is. Then the 2 is a stretch by 2 units. And then finally, we'll take the whole picture and move it up by 5, right? So that's what we should have in mind for the graph here of what we're seeing. But the question is not to find the graph of this or sketch the graph. Instead, it's just to find the vertical asymptote. And here, you should set something equal to 0, right? What should we set equal to 0 in order to identify that vertical asymptote? Yeah, it's whatever's between the parentheses, whatever is being input into the logarithm, right? Because when that hits 0, it's undefined, and you get this big blow up that goes up to infinity. Okay, so here we would do x plus 4, and then we get x equals negative 4. And so bam, there it is. We've written down, without graphing this thing, its vertical asymptote. And we could go through and now graph it and that sort of thing. But notice we could also do the domain. So the domain here is a little more subtle. You have to have an inequality. Here we would say x plus 4, the input into that logarithm, has to be bigger than 0. And then we would go through and solve that. So we get x is bigger than negative 4. And then we could write that as the following interval, right? So they're not asking us for the domain in this case, but I'm just writing it out. It's going to be from negative 4 to infinity. And then finally, the range is the easiest one. It doesn't really, it's not really influenced by anything when we're sort of moving a logarithmic function around, because the range started out being negative infinity to infinity. So when we move it all around, it stays negative infinity to infinity. Okay, so that's that guy. And then with that said, let's now do this one. So this is similar sort of thing. We now have a base e. So ln, remember, is the natural logarithm. And so it's the base e logarithm. And here again, we want to find that vertical asymptote. So where is that? What's the equation for it? No need to graph it. Well, so we want an equation of the line, and the x minus 1 is what we want. Yeah, exactly. So we set x minus 1 equal to 0, but remember, we want an equation for the vertical line, so there we'd have to actually solve for x, right? And therefore, there's a vertical line there at x equals 1, and that's because the whole graph has been shifted 1 unit to the right. Shifted 3 units up and 1 unit to the right, but when we're writing down the vertical asymptote, bam, there it is. And then just to end this with what's the domain, let me remind you here, the domain is when x minus 1 is greater than 0. So you get x is greater than 1. So this domain is 1 out to infinity. Okay? Anything bigger than 1, you can plug into this formula. Anything less than 1, you won't be able to plug in, because, for example, if I plugged in -2, I'd get -2 minus 1, that'd be -3. And then in my calculator, I'd say, okay, what's ln of -3? It would just tell me that's an error, right? There's nothing you can raise e to the power of to get -3. So it's not in the domain of this particular function. Okay, so that's the domain, and then the range again is -infinity to infinity. So that's the 50-minute mark, and I think I'll just go ahead and stop there. Remember, you have a section for 6.3 and 6.4. And if you've already done 6.3, you should go back and check out question 11 and 22 to make sure you understand the details. There was an error there. Okay, have a nice day, guys.